The asynchronous session 1. So in this you'll be learning about tuned amplifiers. So what are tuned amplifiers, and what is a single tuned amplifier, and what are the advantages and disadvantages of the single tuned amplifiers and its applications. So coming to what is tuned amplifiers. So before we know that, a simple amplifier circuit is nothing but it is going to amplify a weak signal. Okay. So when you come to a tuned amplifier, it is nothing but an amplifier circuit which is going to amplify a weak signal at a particular frequency. So these kind of tuned amplifiers will actually consist of a LC circuit, which is also called as a tank circuit or the resonance circuit. Okay, and the resistive load will be, or the collector resistor will be replaced by a tuned circuit so that it can amplify the signal over a narrow band of frequencies, or we call it as center frequency or the resonant frequencies, right? So this circuit is mainly used for amplifying a signal over a slight band of frequencies. That is a narrow value of frequencies that are located at the resonant frequencies, right? So we all know what is resonance, and we know what is the resonance formula. So we know that XL will at resonant frequency, okay, at resonant frequency we have XL equal to XC, right? So the resonance formula here will be equal to 2 pi FL. So XL means 2 pi FL will be equal to XC, means it is equal to 1 over 2 pi FC. Or we can say that the resonant frequency can be derived by using, can be calculated by using this formula 1 over 2 pi root LC. Well, this is the tuned amplifier characteristics. So as already discussed, the tuned amplifier selects and amplifies a signal frequency from a mixture of frequency in any frequency range. Okay, so a tuned amplifier will employ a tuned circuit. So instead of your RC, that is instead of your collector resistor, you're going to connect a C and L circuit, and it is used to tune the different frequency value, right? So here it uses a phenomenon of resonance. So the tank circuit, which is capable of selecting a particular value of frequency, or relatively a narrow band of frequency is being selected, right? So you're going to tune in such a way that you can select a particular value of frequency, or frequencies which is falling under a narrow band of frequencies, right? So the center of this frequency band is a resonant frequency of the tuned circuit. So we all know that FR is nothing but the center frequency, or it is called the resonant frequency, which is given by 1 by 2 pi into root LC, right? So you're going to have either the capacitor and inductance value which is connected in series, or it is going to be connected in parallel. So these are the various classifications of your tuned amplifier. So we have small signal amplifier circuits and large signal amplifier circuits. So under the small signal amplifier circuit, we're going to have single tuned amplifier and a double tuned amplifier. And under the large signal amplifier, we have learned about what is class B, what is class C, as well as what is a push-pull amplifier circuit, right? Well, this is a simple construction of a single tuned amplifier circuit. So if you could see very well here in the circuit, we are going to have a BJT device. Okay, we are going to use a semiconductor device. So either you can use BJT, or we can have FET, or we can have MOSFET. So in this circuit, we have taken a simple bipolar junction transistor, right? So now, as we all know that this is the R1 and R2, right? This R1, R2 and this RE will give you the voltage divider biasing, right? So we have already learned about what is voltage divider biasing and what is the need of biasing in a particular amplifier circuit. So this R1, R2 and RE is going to give you the voltage divider biasing circuit, right? Now, why exactly, or why we go for this voltage divider biasing, keeping all this R1, R2 and RE is nothing but to keep your operating point in the center of the load line. So we all know that how important the operating point is, how important it is in a amplifier circuit, right? So definitely we need to make sure that this operating point is in the center of the load line, and we have learned to draw how to draw a DC load line and an AC load line, right? So here instead of your RC, like I mentioned, instead of RC, right, your collector resistor, I'm going to connect a LNC circuit which is in parallel. So why we have connected this in parallel, and why we can vary this is in order to have a selection so that the resonant frequency what we are getting will be equal to the frequency which has to be amplified. Okay, so we are going to give a signal here and we need to amplify the circuit, and we should make sure, or we need to tune the circuit, that is the LNC values in such a way that the LNC are selected in such a way that the resonant frequency will be equal to the frequency of the frequency which has to be amplified. Okay, so and also we have here one capacitor here, that is let's say it's C1. Okay, let's say, one second. Okay, so let's say it's C1. So this is the coupling capacitor which is coupled to the base of your transistor, right? So C1 is the capacitor which is going to be coupled to the base of the transistor, and this CC is the coupling capacitor which is going to couple to the load resistor RL, right? And CE, that is your bypass capacitor which is connected to the emitter terminal, is nothing but why it is being connected we have already learned. So the bypass capacitor is given in order to have the emitter current to ground and increase the value of the voltage gain. So we should know, or we need to understand that the voltage gain of the circuit has to be higher in order to get a amplified output, right? So that is why we need to have a bypass capacitor which is connected to the emitter terminal, so that the emitter current will be passed to the ground, and it is going to increase the value of the voltage gain, right? So this is the circuit model or the construction of a single tuned amplifier circuit. So this is the explanation of what I gave you regarding the construction. So the single tune amplifier circuit diagram with the capacitor coupling is shown, and we are using the bipolar junction transistor. So the values of LNC can be varied, and it must be equal to the frequency signal which is applied and which has to be amplified. Okay. Well, again, this is just the outline of the construction. So the output of the circuit can be attained by using inductive and capacitive coupling. And this circuit uses capacitive coupling, and you can vary the value of capacitor so that we can get the resonant frequency, and we can maintain or tune the value wherein we get XL, that is your capacitive reactance will be equal to your capacitive inductive reactance value, right? So this is the R1, R2 and RE are the resistors which are given in order to have the voltage biasing. Okay, and also it is going to stabilize the circuit, right? So this is the construction. So coming to the operation of the single tuned amplifier circuit, the desired signal, right? So the signal which is given at the input side required to get amplified must be applied as the input, right? So we are going to have a signal value which has to be amplified, and that is being given to the input of your single tune amplifier circuit, right? So by varying the value of the capacitor, right, by varying the value of the capacitor, we can actually vary the value of the frequency, right? So when you're going to vary that, when your XL is equal to XC, we are going to have the resonant frequency which is obtained, right? So the radio frequency signal which has to be applied to amplified will be applied at the base of your transistor, right? So through your coupling capacitor C1. So you're having a coupling capacitor C1 and you're going to apply the input signal to the transistor through this coupling capacitor C1, right? The value of your resonant frequency of the signal which has to be amplified will be got by varying the value of your capacitive value, because here we saw that uh, the variable component is going to be the capacitor. So keeping the inductor fixed, we can vary the value of the capacitor. So the frequency will be adjusted in such a way that by adjusting the value of L and C, right? So since L is fixed here in the diagram, we can vary the value of C, and when your FR, that is FR means when your 1 by 2 pi root LC will be equal to your input frequency, then you're going to get the maximum value of output at the load resistor. So when am I going to get the maximum value of output at the load resistor is when my resonant frequency, that is when my FR, that is equal to 1 divided by 2 pi into root LC will be equal to the input frequency, then I'm going to get the maximum value of output which is available across the load resistor. So this is the voltage gain and frequency response of your single tuned amplifier circuit. So we can calculate the gain by using the formula, that is gain value AV will be equal to beta into RAC divided by Rn. So here RAC is nothing but equal to, resistance is nothing but equal to L divided by C into R. So replacing this RC in this first equation, I can get what is the value of your voltage gain in the in the circuit, right? So your AV will be equal to beta into L divided by C into R into R input value. That is the input resistance value you're going to calculate. So we can find out what is the internal resistance value, what is RAC value, and keeping that RAC value is nothing but L divided by C into R. So substituting those values, we can find out what is the gain of your voltage gain, and the frequency response can be plotted. So here if you can see, there are lower end frequencies F1 and higher end frequency F2, and the one in between is nothing but your resonant frequency, and at resonant frequency I'm going to get the maximum value of voltage gain. So now this voltage gain will be in terms of dB, right, decibels, right? So it is going to be in terms of decibels, and we also can notice that let's say that this is the point A, and this is the point B, okay, this point. So when you take these 2 points, that is A and B points, these A and B points are called as a half power points, where the value of power is going to be half of the value of your resonant frequency power, okay. So these are called as half power points, this A point and B point, right? So at FR, I'm going to get the maximum value of the output at your load end. So these are the advantages and disadvantages of your single tuned amplifier. So the main advantage is we can select the value of desired frequency by using this amplifier, and we can have a higher value of gain factor due to the cascading phenomenon. So we can also have different cascading options in the single tuned amplifier. So why we do the cascading is in order to have a increased value of gain factor, right? And the disadvantage of single tuned amplifier is its potential instability will be occur due to the reduction of the bandwidth. So we all know that it is for a narrow bandwidth value. So since it's in a narrow value of frequencies, the stability factor will come into picture. So that is, instability of the system can happen due to the narrowband frequencies. So the main applications of single tuned amplifier circuits is in radios and televisions, and the radio frequency amplification circuits will definitely make use of these kind of single tuned amplifier, right? So these are the different applications of your single tuned amplifier.